Okay, so yeah, do you want to just like quickly introduce yourself, just like who you are, where you went to in a university?
Sure.
I mean, it's pretty obvious what institution you're at, but yeah, go for it.
Yeah. So my name is Justin Dubois. I'm a professor here at Stanford for 25 years. I'm in the Department of Chemistry, but I also have a courtesy appointment in the Department of Chemical and Systems Biology. I was an undergraduate at UC Berkeley back in the late 80s and early 90s, where I received a degree in chemistry. From there, I went to California Institute of Technology, Caltech. Where I did 5 years of study to receive a PhD. And then I headed to MIT for 2 years of postdoctoral work and was fortunate enough to get a job here. So you could say this is the first real job that I've ever had. Prior to that, I did odd jobs as a high school and college student. But yeah, so that's my journey to this position.
When I hear look at Caltech and MIT, I'm thinking really prestigious schools that I probably have like no chance of getting into. So that's
I wouldn't say that. One thing's for sure. I mean, getting into an undergraduate
Mhm.
university these days is challenging, but there are many great universities in the United States, and I think we put too much of a premium on Stanford, Caltech, MIT, Harvard. You can get a fantastic education
Yeah.
at many places, and I would also qualify that and say, education is what you put into it. Turns out getting a PhD in STEM, there's, maybe not surprising, there aren't that many people who want PhDs in STEM subjects, and so actually getting into grad school is not nearly as competitive as undergraduate or other professional schools like medical school or law school.
Mm.
So
That's good to know. And yeah, I'll definitely keep that in mind as I continue on
the
my journey.
The other thing I would share with your readers is that students who go to grad school in STEM are paid to go to grad school. So my students make $54,000 a year doing research just about full time. They spend their first year taking some classes and serving as teaching assistants. But for the most part, their experience is really coming to lab, working on research problems, and as I said, they collect a salary for that. It's not a fantastic salary, but it's not bad when you're a student, and education is free. They're not paying a dime for of Stanford's tuition to get a PhD here, so it's a pretty good deal.
Yeah, I would say as well.
Great question. So I went to Cal when I was 18, like most people, right out of high school. Didn't really know what I wanted to study at the time, though, and managed to kind of stumble into the STEM classes in my sophomore year. And then I discovered research. I found myself in the lab trying to fashion molecules together, if you will. I mean, it's a little bit like sort of building, but engineering, but at the molecular level. And I just loved everything about the lab. It was just really a place where everything I was learning in class sort of came alive for me. I could see the real world application of the things that I was learning in my courses. And I loved the culture of the lab. The people there were very kind to me as a young researcher. And it reminded me of being a kid who liked to spend time in the garage building things and working on cars and various other automotive, machines. And but all of that's macroscopic. When I was doing chemistry, of course, you're manipulating atoms and molecules on the microscopic level, but at the end of the day you can see the fruits of your labor in the form of the kinds of powders and liquids and gels that you synthesize, and to me that was really exciting at the time. I had no thought, though, that I would end up getting a PhD degree in chemistry, nor did I have any thought that I would end up as a professor at Stanford. It was really just a curiosity, and I would say, falling in love with a subject that I wasn't aware that I had really any aptitude for, and then just kind of following that interest through grad school.
Yeah. I know you like covered it a little bit already, but I was just wondering, like, currently, what is your like just purpose and mission of your research? And like, if you would like to like share some specific research papers that you
Sure,
really enjoyed.
sure. Yeah, my training is as a synthetic chemist, and what I would say of synthetic chemistry is that, this is the uniqueness of being a chemist. Chemists are really the only scientists who who really design and build new molecules and materials. And it's an incredibly creative science. And I think that's something that we don't share enough with young people. I think they have the sense that chemistry was sort of all figured out 100 years ago or 150 years ago, and there's nothing new to learn or discover, and nothing could be further from the truth. So I cut my teeth as an undergraduate and a graduate student learning, the craft of chemical synthesis, if you will. But I had always been interested in problems that nature solves. Nature's a master chemist. I mean, the number of chemical reactions that are taking part in you and me right now is extraordinary. And how nature manages all of that, how nature selectively manipulates specific molecules, the kinds of molecules that nature creates, all those things interest me. So what am I doing today at Stanford? Long time ago, we got interested in chemical toxins that are found naturally. The most famous one or infamous one is probably that associated with the Japanese pufferfish, the fugu. The molecule is the poison of the fugu is a small molecule called tetrodotoxin, and it's been known for some time. Poisonous nature of the fish has been known since antiquity. The molecule has been known since the 1950s and 60s. And it actually serves as an incredible research tool for scientists who are interested in understanding electrical conduction in nerve cells because it acts by basically blocking electrical conduction. In fact, the value of this poison to researchers interested in a class of proteins known as ion channels is profound. And what my lab did early on in my career at Stanford was to find ways in which we could construct this poison and related poisons through chemical synthesis. So starting with simple starting materials, in one case, it was an amino acid. In another case, it was vitamin C. And we can manipulate those compounds through multiple chemical transformations to make these poisons. Why would we want to do that? Well, at the end of the day, synthesis gives us the opportunity now to to form novel versions of these poisons that nature had never conceived of. And so we can use these poisons now to develop tool compounds that will allow us to look further at the process of electrical generation in nerve cells, and more specifically, something called nociception, which is a fancy word of saying pain sensation. So my lab is really ultimately interested in understanding kind of the molecular underpinnings of pain sensation and the role that ion channels play in pain sensation. And we use chemistry and chemical design as one of the many tools to study this rather complex biochemical process. I hope that makes sense.
Okay, I'm just gonna try summarizing it. So basically, it's like you have this, I'm thinking like pufferfish toxin. I believe like it blocks the ion channels and that prevents like depolarization of neurons. So then,
Yep.
could that be used like in stopping like pain flow or pain medications? And is that
In practice, it can, and it is not tetrodotoxin, I should say, the poison of the fugu actually has been put into human patients in clinical trials as an analgesic, a pain medicine. Other molecules like it are being tested, and then there are well-known ion channel inhibitors. They're not derived from poisons per se. They're actually derived from cocaine, which is the original sort of analgesic that was used back in the early 1900s and even late 1800s to treat certain types of pain in surgery. From there, chemists evolved or developed other canes like lidocaine and novocaine, molecules that I think probably most of your readers are familiar with if they've ever been to the dentist and they've had their gums numbed before any kind of surgery. That was actually a molecule it's sort of derived from cocaine or evolved from cocaine, and that acts as a sodium channel blocker, one specific family of ion channels. So there are ion channels for sodium, potassium, calcium, chloride, and other metabolite, but those are the principal four classes. So yeah, it's quite interesting. And the idea of developing, what I see my lab doing is very basic science and really trying to understand the molecular mechanisms for electrical propagation in nerve cells and for for pain sensation. But we hope that this work would help advance, better medicines for treatment of pain, something that I think we as a society desperately need because, as I'm sure most of your readers know, the drugs we use to treat pain now are highly addictive, things like Vicodin and tramadol, and we really need to find better ways of managing folks who have various types of neuropathies and chronic pain. So it's a big unmet medical need right now, and it's something my group is interested in. But I work with a small company that was spun out of my lab that is doing that kind of research. As I said, in an academic setting, a small group like mine is better positioned to answer basic questions in science, and the heavy lifting and cost of drug discovery is, in my opinion, needs to be done out, in a private sector setting where you have a huge amount of money to capitalize those kinds of efforts.
That
Yeah,
gave me a really good overview of your research. Like,
sure.
so what were the biggest challenges you faced in research so far, and just like what steps you take to overcome those?
Oh, wow. Yeah. Research moves in fits and starts. So I would say every day there's a different challenge that presents itself. Unfortunately, I think it's fair to say that a large percentage of what we do doesn't work the first time, the second time, the third time. And so, there is a lot of design build test, if you will, cycles that we go through, where hopefully we're learning from the experiments that didn't work out the way we wanted to, and then we're using that knowledge to obviously try and improve our chances on the next go round. But one has to be tenacious in this business, and understand that science is hard, and it moves incrementally. So I would say just in general, those are the challenges. As a researcher at Stanford and as somebody who's also in the classroom teaching undergraduates for the most part, and sometimes graduate students, I think there are some terrific challenges. As an educator, one of the big challenges is getting young people to get excited about chemistry. Unfortunately, the subject does not exactly inspire, a lot of people to get out of their chairs, and I think, chemistry has the tradition of being a very hard subject, and so a lot of students that I meet are pretty scared about, having to take several classes in chemistry as requirements for other, STEM majors that they might be interested in. So I think trying to get the message across to young people that it's a wonderful science. It's foundational for understanding a whole lot of other science, because at the end of the day, we are just molecules. Um, and I think really giving students an appreciation for the beauty of the language of chemistry is something that I feel challenged by. Uh, in the lab, I direct a group of PhD students and sometimes postdocs, and occasionally we have undergrads working with us. Often, frequently, we have undergrads working with us. And so, managing a diverse group of individuals who are all working on different projects is a challenge, I suppose. I mean, I love the challenge of that. I love working with young people, and helping them find and discover the kinds of projects and research interests that they have, and then watching them struggle with a problem for a while, but eventually have success. That is incredibly rewarding part of my job. So as much as it is to see a young student, a young undergrad at Stanford get excited about chemistry and start to see the light bulb go on, like, why is this subject so interesting and relevant? That's also incredibly rewarding. So, yeah, long answer to your question. I'm sorry.
It's all right. I can definitely relate to like I think both of your topics because I do research on like plastic degradation, and a lot of my experiments have been failing. I'm not sure it's because basically I just like take plastic enzymes and like genetically engineer it into bacteria.
Yeah.
Yeah, and then we're not sure if the bacteria is like the bacteria is not able to take the byproducts of the enzyme and digest it, or if the enzyme is just not working with a specific type of plastic. But for whatever reason, it's not working. Also, for chemistry, I can definitely because like in chemistry at our school, it's taught like I guess you could say block by block. It's almost as if it's like set in stone. I can definitely see
Yeah.
how
Yeah.
that sort of like takes out some of the interest in chemistry. Like I think
Yeah.
your conversation really sparked a lot of interest in me.
Yeah, no, I really would want young people to see chemistry as molecular architecture. You know,
Hmm.
we are the only, again, we are the only branch of science that designs molecules, and the power of that is awesome. I mean, you know, when you think about agrochemicals, when you think about the pharmaceutical industry, when you think about any kind of material science, it has to start with a molecular blueprint. And that comes from the mind of a chemist. And I think that's just lost on the large body public. I mean, you know, I don't think most people associate even pharmaceutical science with chemistry. I think they think it's biology and medicine, but nothing could be further than the truth. I mean, the people who actually design new drugs are chemists, and they come from labs like mine. So I have many former graduate students and postdocs and undergrads who are in the pharmaceutical sector. That they are on the sort of front line, if you will, of drug discovery. I myself have the benefit in this job of working with a number of pharmaceutical companies as a consultant. And, what is my role there? It's really to help think about how to design and develop small molecule drug therapies. So I feel like we chemists just haven't done a good enough job of really impressing upon young people just how impactful it is to be able to take the building blocks, that is the periodic table, and to organize atoms in different ways to design to advance new structures with new function. That's really the as I see it, the beauty of my craft. So
I actually have like two questions. Which
yeah.
person or mentor in your field made like the biggest impact to you for your research? And were there any like pivotal moments in your research career that made you want to like change topics or pursue a certain topic?
Oh, yeah, interesting. First one's pretty easy. It's more than one for sure. I mean, I had some fantastic teachers at UC Berkeley. A fellow by the name of Alex Pines. He was just such an inspiring lecturer. I had him for the first semester of general chemistry, and I honestly, to this day, don't understand how you could make titration curves and acid-base chemistry so interesting. But this man did, and I really found myself reaching for my chemistry homework first. And I say this to Stanford students, when it comes to choosing a major, you know, I think we overthink these things sometimes. My first question to them is, when you have a stack of homework, which homework do you like doing first? And I think I realized in a moment that was kind of the answer to my question when I was 18 or 19. What major do I want to, study here? Well, I was always going for the chemistry, first. And so, um, again, that may be a sort of somewhat trite way of saying, of choosing one's major, but I really do think people should choose subjects that they love first and foremost, and everything else will sort of follow from there. I think sometimes too many students are worried about getting a job after college, and they choose their major accordingly. And I get that, but I think you should study something you love. So my undergraduate instructors, Alex Pines was one, but I had several others there. My undergraduate research mentor, a fellow by the name of Ken Raymond, just a wonderful, wonderful human being who just, gave me so much opportunity in his lab. And the people who were in that lab who then mentored me on a sort of day-to-day basis, if you will, really showed me how to do chemistry. And then my PhD advisor, a fellow by the name of Eric Carrera, was hugely influential in my life, a dear friend. And so I would say, from the standpoint of the people who have impacted my professional career, those would be the individuals. And of course, like most of us, we all have parents that we should be grateful for. I'm very grateful for mine. They fostered a curiosity and a love of learning. And I honestly don't know how they did that, but that's that's the person I became. So I'm grateful to them for that. A grandfather who was incredibly inspiring as well. Second question was,
Like pivotal moments in your research career that like make you want to pursue a certain topic or maybe change topics.
yeah, I've really my career has really pivoted from being almost exclusively focused on synthetic chemistry and the synthesis and development of syntheses to natural products, the development of technologies that would facilitate the assembly of molecules. And now these days, my lab is, I would say, much more heavily focused on problems that interface chemistry and biology and biochemistry. So that I think what happened to me along the way at Stanford is that I saw opportunities for us to work with people at the medical school. The medical school sits literally across the street from my labs. I saw opportunities to go after these kinds of, maybe larger problems that would have more of an impact on society. If we could actually discover new protein targets that could be potentially drugged, if you will. That is, in the spirit of sort of developing next generation pain medicines, could we identify targets that would not lead to addiction and have all the added, sort of baggage that opioids have. So I was looking for problems like that, and I was fortunate that along the way, I got very excited about ion channel research and then found an opportunity to sort of marry my interest and my passion for designing and developing small molecules with a larger problem in biochemistry, where I thought these tool compounds would really be invaluable for studying the biochemical mechanisms of pain signaling. And that's a bet that I'm still playing. I'm still playing that hand right now. I mean, we're in the process of really still trying to advance these tools, validate that they work as we would like them to, and then really go after specific questions and associated with pain signaling with nociception. So yeah, I think I'm long answer your question again, but I feel like my career really pivoted about probably 15 years ago, where we started to really move hard in this direction of chemical biology as it's called. Yeah, along the way, I suppose earlier in my career, I moved from my graduate studies at Caltech to my postdoctoral work at MIT, and I did change directions there as well. As a grad student, I became really interested in oxidation chemistry. So how does nature use O2 to actually oxidize fantastic precision specific molecules, molecules that you and I would otherwise, eat as part of our diet, or that are just part of our primary metabolism, and that nature has to do a number of wonderfully selective oxidation reactions. And trying to understand that in greater detail was something that fascinated me. It was very different from my work as a grad student. So I postdoced in a lab where that was a focus. I think those are the times I get very excited about other people's science. I really love learning about all kinds of science and material science, enzymology, physical chemistry. I don't know that I've ever had a desire though to completely uproot what I'm doing and move in a totally different direction, because at the end of the day, what I love the most is again our ability to design and develop new molecules with new functions, and then to use those chemical tools again to study larger, more complex mechanisms. I find that incredibly fascinating and rewarding as a problem area.
Okay, I can definitely understand that. I focus more on biology, and it's been like my pathway for a while now.
Yeah, yeah. And I think what I see in the biochemistry students I teach, a lot of them are interested in biology and human biology. And I think what I hopefully am able to share with them is just that at the end of the day, I mean, we are nothing more than a big bag of chemicals. And, all human action can be understood at the level of chemical reactions and thermodynamics and kinetics. kinds of things we learn in general chemistry and organic chemistry. And I understand that we don't, we have plenty still more to learn, especially about the 3 pounds of matter that sits between our ears. But I have no doubt as a chemist that it will all come down to chemistry. It does. There's no other explanation for it. So as far as I'm concerned. So that's something I feel like, yeah, it's easy to get excited about biology when you're a chemist, and I would hope that it would be easy to get excited about chemistry when you lean towards biology. There's a wonderful, opportunity to span those disciplines like many of us do.
So what kind of like skills would like a great researcher have? Like what kind of skills do you think that like, that you would look out for or like that you think were really important in your career? And how would high schoolers like develop those skills?
Yeah. I don't know if it's so much a skill, but enthusiasm is line one for me. I mean, people just have to be really excited to be in the lab environment. I mean, it has to be a passion. It cannot be viewed as work. I think for me, work was flipping burgers at Burger King. That was work. I came in at a certain time of the day and I left at a certain time of the day, and I was happy when the day was over. I think for successful researchers, the lab is just a haven where they want to spend their time, and they get excited about trying to push the envelope of science, and they're doggedly determined to solve the problem. That the trials and tribulations of research, the quote unquote failures, I don't like to call them failures because you're always learning something, but the experiments that don't work the way you want do not dissuade you from coming back the next day and trying again. In fact, if anything, it just makes you sort of tighten your belt more. So I think those are the most important things. I mean, I don't think anybody should do research just because it looks good on one CV. That would be a huge mistake. In terms of the skills, I think common sense, honestly, is number one. And then, having an eye for detail. I think most discoveries are not planned. They are not premeditated. They are serendipitous, and they come because a researcher saw something. They were looking for one thing, but they saw the hint of something else, and they followed their nose to that, and that led to something awesome. I'd love to tell you that all discoveries are pre-planned. We're all so smart and clever that we can figure things out. It's just not the way science rolls. There's so much serendipity. And so being curious and being diligent and being meticulous are all great skills. I don't know if they count as skills or as more like, qualities or characteristics, but I think that having enough technical training to that and reading the literature broadly so that you can see the connection, or you have a sense of how perhaps a discovery you make could connect to a problem that may not even be the one that you're specifically interested in, but that can be where you have the biggest impact. And I think for my money, that's something I really try to encourage my own coworkers to do a lot, which is to go to lots of different kinds of seminars, to read the literature broadly. I don't know if that answers your question specifically. Background and training is important, but honestly, the technical aspects of doing research can be instilled pretty quickly in a young researcher. I can teach you very quickly how to operate in a lab, how to mix chemicals, how to follow reactions. I think it's more about, again, being well versed enough in the science and having broad enough knowledge in other science that you give yourself an opportunity to make a really fantastic serendipitous discovery. As I like to say to my coworkers, I mean, we work hard to give ourselves the opportunity to be lucky. That's really kind of how science rolls. We put ourselves in a position where one day we'll have that fantastically lucky break, and we'll be there to recognize it.
Yes, I was just wondering where did you get your first taste of research? Did you start like at a basic lab position? Did you have an internship? And yeah, that's just
Yeah, yeah. I should say that my father was a high school science teacher, and back in the 70s, he had a phenomenal lab. And as a young kid, I would go to his office, and he would once in a while show it, do a demonstration for my brother and me. And so I don't know I can't say if that really was the seed that was planted at the time, but I certainly remember those demonstrations vividly. When I was at Berkeley, I was a sophomore, and I remember having a friend in the dorms who told me about the research he was doing. And at the time, I was really naive. I didn't really know what that meant. And he said, yeah, was working in a lab outside of his normal courses where he was able to do experiments. And I thought that sounded really interesting. So I started talking to my graduate student TAs in my various classes, almost begging them for a position, as a dishwasher, if nothing else, just because I thought this would be a fantastic way to spend a summer up at Cal, and not have to go back to my parents' house for the summer. And I was fortunate enough to have a TA, who then put me in touch with his mentor, his PhD advisor, this fellow named Ken Raymond. And I got my first taste of doing research there, and I stayed in that lab for the following 3 years, and I just really, again, loved the experience. I was very fortunate. So I think every undergraduate at every university should get an experience of doing research outside of their normal coursework, and it doesn't have to all take the form of chemistry laboratory research. There's so much research going on at any university campus or college, and I just feel like having an opportunity to do some kind of independent study like that is really a transformative experience for young people. So we try to do as best we can as a small lab to bring in as many undergrads as we can who want similar experiences. And some really take to the science, and others find out that it's not maybe for them, and then they go off and find a different research position. And that's great. That's something you should be doing as an undergrad, because again, the campuses that you're on are so diverse with interests. You should try to take advantage of that, and find, what it is that really makes you want to get out of bed every morning and run to quote unquote work.
Thank you so much for your time today. It was really enjoyable talk with me,
Oh,
for me.
it's a great pleasure.